Hi, this is Ari Everett for CSC120 in the fall of 2023. This is my demonstration for quiz 6. I chose to use the one hot encoding question within the quiz because I thought this is a good example and demonstration of my understanding. Not using a one hot encoding would, I think, reduce the complexity and not a good demonstration of my understanding of this concept. Plus, personally, I did want to build this system out because I've not yet personally built a one hot encoded system. So we'll look at the constraints here for the design, the problem statement and goal. And on the right, I have the circuit running. So we were to build a stoplight that's on a timer, 3 lights, green, yellow, red. There's a separately programmed timer that we don't have to worry about. Use one hot encoding and D flip-flops. No emergency signal for this one in case an ambulance comes. So I started with the design algorithm and mapped that out. We have our state diagram, then select flip-flop and transition table, then build the next state table, Boolean equations, build and test circuit. Here's the state diagram that I created. It is green, yellow, and red, color-coded to make it easy. Since it is a one hot design, only one state can be high at one point. So with 3 different states, we'll need 3 bits. Green is 001, yellow 010, red is 100. In our flip-flop table, the constraints are to use the D flip-flop, and here's how the transition table looks like for D flip-flop. Next state table is the present state, next state, and then the flip-flop inputs to get from present state to next state. The green has 2 different states it could be in, or 2 different inputs with X here. X is noted by these lines right here from the state diagram. 1 will push us forward in the process, 0 will stay put. So since there is 0 and 1, each state code has 2 states that it could be in. And 0 it will stay, and then 1 it will go to next. So to build this out, green at 001 with an input of 1 goes to yellow in its next state, 010. The flip-flop inputs needed for that are 010. When you look at D2, just look at the Q2 columns. It went from 0, present state, to 0. So based off our transition table, it stays at 0. This one, Q1, went from 0 to 1. Based off our transition table, 0 to 1, you need a D of 1, so that's a 1. Process is repeated here. If we were to add more colors and more states, this table would get longer, and then our Boolean equations and our K-maps would be longer, more complex, and we get into some 5 input K-maps. Next, we'll derive the Boolean equations. A couple things I did to prep for that was I circled the FF inputs for those flip-flop outputs with 1s, which would be the 1s in our K-maps, and then 2, I put the don't care states down here. Since we have now 4 digits, or a 4-bit input for a K-map with the X input and 1, 2, 3 flip-flops, that leaves a lot of don't care conditions that we didn't list in the table because we don't care about them. Those states are not used in the one hot encoding. So in 1 here, for example, is 000 and then a don't care within the don't care. So 0001 and 0000, you can see from up in this table, is not used at all. So I built out the K-maps here. The red X's correspond to the red don't care states. And then you can see the green 1s correspond to the green circles. Color-coded, we grouped as many of the largest groups as possible with green and this pink. Down below are the eliminations and retainments of the K-map rules and laws to build out these formulas for D2, D1, and D0. Step 5 was to build it. So on to the build. We have the major components of a more sequential circuit. We have input, state memory, which are the flip-flops, next state logic, which also doubles as our output logic, and then our output here. I say it doubles as the output logic just because this is a Moore machine, and the outputs and the one hot encoding allow for a direct output of the flip-flop and no decoding, output decoding going to the output. So how I started was I dropped in the flip-flops first and worked my way to the next state logic by looking at back here the Boolean equation. So D2 is Q1 and X or Q2 and X naught. So you can see here, Q1 and with QX, and then Q2 ANDed with X naught, and then the OR outputs the D2. This tunnels D2 input to the flip-flop, our clock to keep us in sync, a reset, and the Q2 tunnels out to Q2 here. This is repeated for the other flip-flops, and this is my final build out. So a couple points of reflection here are we need to make sure that the next state table and Boolean equations are correct. And furthermore, the state diagram, so this impacts everything downstream. I had one issue in making the build where I had to go back to the next state table to ensure that this was all correct. Using tunnels in Logisim was much better. And so what's cool is I found this button in Logisim that is both a momentary and latch button. So when I click and hold it, you can see the flip-flops even as the clock goes round and round. Oop, I went off of it there, sorry. Let me get into poke mode. I'm pressing and holding the mouse now, so this is a latch mode. And look at the flip-flops, they're 0, 0, 1, and it's in that green state, even as the clock goes through and tries to push this through. Then I let go, and it will continue to do that. Or I can just momentarily click it, and it'll reset to green. You can see it's going back to green whenever I do that. A couple things that I could have done to expand this, or in some iteration and next versions for it, are to actually build out a timer for it. You could build out an asynchronous or synchronous counter that attaches to this clock or replaces the clock to put it on a timer system or a counting system that could go off of the counter rather than syncing the clock or choosing a clock slow enough to make this an applicable timer in the real world. You could add an emergency button for when emergency vehicles drive through and we'll push it to red. You could also add some more colors if you needed to as well. And that's it for my design. Thank you.